Okay, so before we look at the Boltzmann distribution graph for a catalyzed reaction, I just want to reiterate some really important principles that you must have tattooed onto your brain. Okay, so number one, catalysts increase the rate of reaction by providing an alternative reaction pathway. This is shown on the right. Two reaction pathways, one which is uncatalyzed and one which is catalyzed. As you can note, the difference between the two is that the alternate pathway, the catalyzed pathway, must have a lower activation enthalpy to lead to a rate increase. Finally, this means more effective collisions between reactants per unit time, as shown on the Boltzmann graphs below. So for two reaction containers, both having identical kinetic energy, so the temperature is the same for both reactant containers. If you have a catalyst in one, although you will not change the amount of energy the particles contain, you will change their ability to react with one another. So the catalyzed reaction will mean that particles that are moving with less energy can now actually react. So let's say that again. The two reactions shown below are happening at the same temperature. However, because there is a catalyst in the container on the right, the bottom right, particles that are moving with less energy are now able to react. By what mechanism will that occur? Let's have a look. So, here is our catalyzed reaction Boltzmann distribution graph. Now, in the reaction container, what we're going to have, and this is interesting because it connects to other concepts in chemistry, what we're going to have is our catalyst forming some sort of interaction. In most cases, this interaction is an IMF interaction. So it could be hydrogen bonding, it can be dipole-dipole, it can be London dispersal forces. Sometimes they form chemical bonds, but not so often. So our catalyst will form some kind of interaction with one or both of the particles. After it forms that interaction, what that means is that that particle which is reacting, in this case B, is being held in place. It is unable right now to rotate freely, and as such, its reactant group, that triangle, is always pointing outwards. What this means is that another particle is able to come in and collide with it in the right orientation. These collisions, these effective collisions, are going to happen more frequently, and the rate of reaction is going to increase. That is only one way in which a catalyst increases the rate of reaction. The other way, and you may or may not notice this, is that when a catalyst bonds to a group, you're going to distort the electron cloud. So when you form an interaction, you're going to distort the electron cloud. Now, I've shown an oversimplification of the cloud distortion by stretching it over both B and C. Of course, if this is forming an IMF interaction, then you will not have electron density from B actually going around C, but what you will have is electron density around B moving slightly in space towards the electron clouds of C. As such, I'm simplifying it here by just showing a distortion of electron clouds. What that means is that there are less electrons repelling other A molecules away from the B triangle. So now there are less electrons repelling other things away from B, and therefore A, while traveling at lower kinetic energies, is able to collide with B and form a reaction. So let's simplify that. What I'm trying to say is that because the electrons that are repelling other molecules away from B are now shifted towards C, there are less electrons in front of that reactant group of B, and A is able to collide with it at lower energies but still overcome the electron repulsions. Please feel free to pause or rewind the videos if you want to hear explanations again. I do my best to try and make them as clear as possible first time. So, this is our enthalpy graph with activation energy with and without catalyst. So with the catalyst, because we have reduced the electron repulsions between the two reacting groups, they are able to react while colliding with less energy than before. This is shown on our Boltzmann distribution graph on the right because there is a larger shaded area of molecules, which means that a larger amount of molecules are able to react per unit time. This makes the rate of reaction quicker. It's important to note that if we were to add enough energy to make both these things react, whether there is a catalyst or not, over time they will both eventually react to completion, or they will react to reach equilibrium. It's just that with a catalyst it will reach that equilibrium point much faster. So just like before, I'm showing you the collisions between A and B. When they happen without enough energy, then as such they will not react. Note that when they do collide on the right with a catalyst involved, the strength of the collision between the two doesn't need to be that much stronger at all. It's just that because there are less electron repulsions with a catalyst, then the kinetic energies of A and B are enough to cause a chemical reaction to occur.